So I'd like to talk about how artificial intelligence could help us find deeper physics. So it's not solving, but just go one level deeper. So I explain what I mean. So there are many claims that people say that they have theory of everything, yeah, but usually they are ignored by mainstream. So there are some likes on social media, but nobody checks it. So because the such verification is very difficult. So, but the main point here is that now modern AI models can rigorously test such claims. So, I believe we should finally just take automatically take all such claims and just verify them. And it's already happening, like in this table below. So maybe let me start with why we should search for them, the motivation. One, there are three main reasons. So one is that there are many problems with current view, like this unification with gravity, but many others also I mentioned. Then the complexity. So now there is this gigantic Lagrangian of standard model and of 30 parameters. So maybe very briefly. So here is the gigantic Lagrangian, and the question is, could we derive some function simpler? Yeah. So it is a very general formula we can fit all. Yeah, so like Taylor series that there is something happening, we just have completely general formula, fit the parameters, we can describe it, but we don't understand what's happening there. Yeah, so we should get deeper expansion, Taylor expansion of what? Yeah, so try to get lower level and try to understand where this huge formula comes from. And more practically, it has like 30 parameters. We'd like to get them from a few. Yeah, so reduce the number of parameters, derive all of them from a few. Then, but finally, this also this understanding that there is presented, so there's used some called perturbative approximation that particles as perfect points. However, in deeper in non-perturbative, they are field configurations. For example, electron has electric field, magnetic dipole moment, angular momentum. We would like to understand these field properties. Yeah, so, and this is maybe still people say that this shut up and calculate is like 6-year-old quote or something, but there are now many new experiments showing that we can understand a lot. So maybe you should no longer try to believe in this understanding impossibility, which is kind of creationism. Yeah, like also then they said that we cannot understand biology. Now they say that we cannot understand quantum mechanics, physics, which is some mental barrier we should maybe at least try to uh, verify, and artificial intelligence can now do objectively. So early there were these LLMs, why physics, nearly unreadable articles, nodos, but they were terrible, and so text and alone is insufficient for language models to work with physics. Instead, we need simulations. Yes, so just text might look nice, but we need to check if given Lagrangian here gives consequences as it should be, as in physics. And this is indeed happening recently with these Fable top models that we know what properties physics should satisfy, and so there are candidates, and we can this it can rigorously test it, perform simulations, and check if the simulations agree with what we know. Yeah, so instead of just working off words, it builds simulations. I've shown some results and checks consequences of the simulations with what we know from nature. So, for example, the most important criterion, I think, is charge quantization, because if there is no charge quantization, then all charge particles will just explode. Yeah, so we cannot say that we have model particle without charge quantization. So here is the current. No, this here's the benchmark. Not very current, but still the best is this liquid crystal approach I will talk more about. Another is by Mark Fleury, this non-computer scientist. Paul Verbos, even better known. So he also he started backpropagation. So the people who worked before on some models, and now there is this kind of benchmark competition. and automatically these models are tested and they are open to for more. So if you have some model, maybe you could add there if there is Lagrangian something we could simulate. So basically we need Lagrangian the formulas to simulate and initial configuration, for example, some approximate of particle. Yeah, so this is the basics to perform this kind of simulations. Okay, so one again, why do we need deeper physics? So as mentioned, there are problems like this incompatibility with general relativity, dark matter, but I think even much more important are the problems like EMC. This is one of problems with nuclear physics. So they try to see large nuclei as built of quarks, as back of quarks, but it completely didn't work. So now they talk about quarks up to proton and neutron. But if you take deuteron, uh, they I haven't heard about quarks about in deuteron, but there are other problems in deuteron. I mean, we know that it has electrical dipole moment plus minus plus. So with quarks, we need some quark deformation, also like this EMC effect. But mainstream, there are these lattice QCD people who claim that have deeper level of nuclear physics, but they are not able to answer any question like charge distribution of neutron, like deuteron, nothing. So I've also talked with people working on nuclei. They get sometimes some models from lattice QCD people, but that doesn't work. So for decades, people say that they do something deeper, but they don't bring any conclusion. So generally, now there are these two worlds. Now, one there is standard model which works for the particles up to proton and neutron, but for nuclear physics there is another huge formula like this: three body forces, four body forces, then some laws of heuristics and universal models. But we don't understand. We have now two models, two worlds: standard model and nuclear physics, which are there is no transition in this moment. Yeah, so even deuteron, the simplest non-trivial nucleus is not derived from lattice Custodian model. So yes, so there are lots of problems now. Yeah, so we need to bridge them. We need some deeper model. I will also mention about these problems to understand the problems and to resolve all of them, to unify all the problems. The second step here is that this is some very general guess and fit. Yeah, so like Taylor series that you have some behavior. You can describe it as close as you want, like it was with these epicycles, Fourier modes. But it doesn't mean that you understand what's happening there. Yeah, so we are here that we can have very general formula, fit all the terms, but we don't understand, that doesn't understand what's happening inside. Yeah, so we should finally get deeper and try to find where this huge formula comes from. Yes, find something simpler, which will allow to derive it. And more practically, it has like 30 parameters. We should be able to derive it from a smaller number, like for example, three parameters in this model I mentioned. So I've mentioned that the M5 liquid crystal is the more the gets the best agreement in this moment, and this is like just this Lagrangian. This is very standard. This like electromagnetics. The potential is complicated. But so this is then the main difficult to find the proper potential now. And the second term is for exactly for charge quantization, starting with charge quantization. That we say that our electromagnetism is curvature of deeper field. This way the Gauss law counts topological charge, which has to be integer. Yeah, so this very simple model automatically unifies electromagnetic quantum mechanical gravity, and with topological excitations get looking right entire particle menagerie from just three parameters. The question is how many parameters are the potential, approximately three, four, maybe five, to derive or 30. Yeah, so this is ambitious goal, but it seems doable. But there are difficult numerical problems, so it's not so simple. And finally, the last motivation for search for deeper physics is that particles are now represented as points, like these Fermat diagrams, because points for electrons, but deeper there are field configurations. If you have electron, then you know there is electric charge around. 1 over distance square, there's magnetic dipole, a tiny magnet, there is some angular momentum, something rotates, yes, and they say that perfect point cannot rotate. Yeah, it would have to we would need infinite and rotation speed. But we have field configuration, it's field is rotating. So this is similar that we can say that apple plus apple equals to apple. This is true, but it doesn't say much about apples. Yes, and we are also we can ask for deeper what is the structure of this apple, and also for particles. For Riemann diagrams, you'd like to ask what is the structure represented by this general algebra for apples, for particles. Yeah, so literally we need kind of new Copernican revolution. Yeah, so that we have these epicycles, this fitted general formula, and now we'd like to get where it comes from, gets from these points like geometries now to fields, which are in fact the central object of modern physics. Yeah, so go from thinking about points into thinking about fields alone. Okay, so finally, here's this most promising Lagrangian in this moment. This potential is still to be found, and the simulations are very difficult. So, if getting right, it unifies electromagnetic quantum mechanics and gravity in one Lagrangian. So it's very difficult to simulate. There are various problems that you have many scales of orders of magnitude of parameters, and we will need to work on them simultaneously. But AI can now help. Yeah, so we have these agents, this one article that it wants to find some neutrino flavor theory design, and so the agents guesses new model, calculates these consequences, and finally compare with what there should be, update the agent. Yeah, so or even more sophisticated, like in this recent article, that we have we have some observations. For us, this is can be this crucial Lagrangian or maybe some specific its properties, and you'd like to find some model which agrees with these observations. Yeah, so we get some planning selection of experiments. Maybe yeah, so maybe again we can also ask for additional experiments, maybe numerical experiments. Yeah, exactly. Yeah, and then compare the results with what you expect. So like here, that if the consequences of Lagrangian are in agreement with what we know about physics. Okay, so here is summary of the properties you would like to test. They are very difficult. If getting all right, yes, I think we could say that we have went one level deeper in physics. Solving, it's not exactly solving, because like we need this potential. Yes, and potential is usually effective. So I would expect that there is even deeper level. So after finding this one, we should search for another one which can explain this potential, uh, derive it. So maybe, so here we need like about 3 parameters, maybe try to derive it from ideally from 0 parameters. Yes, so the question is, there is this anthropic principle that slightly changing some parameters, the humans couldn't life, there would be no life. But if you reduce number of parameters, it becomes more complicated. So again, we should rethink it. Maybe the probability is much larger. Okay, so maybe let's briefly go through this. So there is, I mentioned the most important is charge quantization. Without it, all charge particles like electrons will just explode. Then there is Coulomb interaction for them. I'm showing in a moment. If having Lorentz contraction, which is believed to be crucial, and having both, it is known from, for example, from Feynman lectures that we need also magnetism. Then there are deformations of Coulomb interaction, like running coupling, and we observe them also in such models of particles. Then we have one half spin. So it says that if we rotate by full rotation, our field rotates only by half. So it means that we need to use field which after rotation by half rotation is the same field, like this ellipsoid. Yeah, so if you rotate ellipsoid by pi, by half of full rotation, we have the same ellipsoid. So using symmetric field, we can get these 1/2 particles. Then we need time crystals. So this is time crystals are objects which are oscillating already in the lowest energy state in the original definition. And we know in particular that there are these three neutrinos and they are already oscillating. So the lowest energy neutrino is already oscillating. Also electron, in the lowest energy, it has angular momentum, something rotates. So now mainstream says some magical, we don't understand, but now thinking about fields, it has to field has to rotate. Then for quantum mechanics, so quantum phase degree of freedom, which has Klein-Gordon-like equation. Then we have magnetic dipole, Larmor precession, yes, so these basic properties of electron. There are also more sophisticated, but I think testing those should be sufficient. Then we have three leptons. So we have we have electron, muon, and tau, which are asymptotically have the same electric charge, but have different masses. Yeah, so why exactly three? For example, because we live in three spatial dimensions. Then we should get the decay I will mention further. Later, we would like to also get the positronium. There are two types of annihilation of positronium, one para or ortho. Then going to nuclear physics, we need proton much heavier than electron, and also neutron, which have nearly the same mass. It's slightly heavier, but it's neutral. Also, for neutron, it is known that it has positive core negative shell. So this is also interesting. We can also anchor our models. Then we have the decay. Yeah, so I mentioned that there is muon tau decay. There is beta decay of neutron, which should lead to proton, electron, neutrino. There is corner potential between quarks. Yeah, so what about quarks? So while we have charge quantization, somehow inside baryons nuclei there are fractional charges. Yes, and we should get the fractional charges. Also, they get this the corner potential. We can explain. Then we have the simplest deuteron. So mainstream lattice custody people are here. So we would like to here go further than currently mainstream can do. Yes, for deuteron, mainstream cannot say anything really from the lattice custody perspective. For example, this electric quadrupole moment, it is plus minus plus. Then we have larger nuclei, but they are quite difficult to simulate. But finally, you should also get simulations, and these are the most practical consequences if getting there. So because it could allow to optimize nuclear fusion, for example. Yeah. So I think there are and maybe there is open question if there is proton decay. So if baryon could decay. If so, maybe there will be a way to stimulate some decay. If so, to be ultimate energy source, literally MC square from any matter. So maybe in 100 of years, we could stimulate nuclear decay. Finally, the best test would be getting quantitative agreement, but it's extremely difficult. For gravity, we need Newton force. Then with Lorentz covariance, we will get gravitational magnetism. Also, we need some other properties like light bending, time dilation. Okay, so here is another summary from this app. So again, in this Larmor precession, here is this rotation that this spin 1/2 that rotating it by. That this is literally well known spin 1/2 configuration. That is if you rotate this configuration by full rotation, the field will go around. The field will rotate by half of full rotation, but ellipse rotated by half is already the same ellipse. So we get the spin 1/2. Yeah, so it's relatively, people say that there's some magic that after if you rotate by full rotation, then you need another full rotation to go back. So this is some magical. So if I rotate fully, another person will do double rotate. We kind of are in different universes. So it makes no sense. Some magic like nobody understands this, but the problem disappears when just going to symmetric fields like here. Okay, so now I will talk more about this liquid crystal approach, why it is considered so promising. So generally, starting from electromagnetics and hydrodynamics, so already they are very similar, especially if there is no viscosity. We need this correspondence that magnetic field corresponds to vorticity, A field corresponds to V, and the formulas are very similar. But we miss charges like electrons. Yeah, so where the elementary charges especially comes from, we need quantized charges. Yeah, so they get them by just topological charge quantization. Yeah, so we have this one topological charge like hedgehog, then the opposite topological charge, and they can say they can look at the distance versus time, and then feed the behavior, and turns out it's close to Coulomb interaction. It's not exactly here, but we get quantized charges as topological kind of electrons, uh, and they get Coulomb interaction. Also, there is, for example, this artic fusion fission that we have also varying size knots, and in particle physics we have varying size nuclei, and turns out this correspondence is quite promising. Yeah, so we need two types of topological charges. One are the point-like, second are the vortex-like, forming knots. Okay, so here is the a bit of mathematics, but just especially this Gauss law. Yeah, so the question is how to get the Gauss law. So there is this question. We have the standard electromagnetism. If you integrate the electric field over some closed surface, it returns charge inside the surface. This is the Gauss law. But the problem is that it returns charge being a real number, while in nature it has to be integer number. So we need to repair it. And this is the central topic, I think, of should be of all such approaches, because without it, again, electron would split into two half electrons, and so it would explode. Without charge quantization, all charged particles would literally explode. So there is topological version of Gauss law called Gauss-Bonnet theorem. Very similar, but now returning the topological charge of some deeper field. Yeah, so we have the field n of unitary vectors. Here is curvature, and integrating this curvature, we get topological charge like this number of winding numbers around, which has to be integer. Yeah, so how to repair the Gauss law? We have to start with some deeper field, like of unitary vector field here, define its curvature as electric field, and this way the Gauss law counts the topological charge, getting the charge quantization. Yeah, so we need this deeper field to have the charge quantization, and that's the main story. Also, I have shown this simple. The second line is saying that this F is curvature of deeper field for charge quantization. Exactly. Yeah. So this way we get the charge quantization, and moreover for liquid crystals, we have this long axis, and its hedgehog is this elementary charge. So here is kind of electron, like here. So electron analog. But finally, we need also this electron also needs angular momentum magnetic dipole. So here is some animation of electron as quantized charge as topological plus angular momentum. There is something actual rotation, but not of point, but of the field configuration of surrounding the electron. Yeah, so by this rotation we get angular momentum, magnetic dipole, also the Raman precession. So it's crucial that we also recognize twists of this long axis. Yeah, so in space we have this long axis forming the hedgehog as its topological charges are electric charges, quantized, but it also recognizes the twists. Yeah, so we need also recognize the twists. So finally, in space we have the high energy tilts for electromagnetism and low energy twists for this quantum mechanics. So turns out they will get this Klein-Gordon-like equation. And finally, we live in space-time. We also at time, and there additionally are required the boosts. And from boosts we get second set of Maxwell equations automatically, which corresponds to gravity to magnetism. So this is gravity. So there are also this. So there is also coupling between such gravity and electromagnetism for slowing down of electromagnetic propagation in gravitational field, what gives them time dilation, gravitational, and the light bending by Fermat principle. Yeah, so we have these three types of field dynamics. Yeah, so these tilts, high energy tilts, low energy twists for quantum mechanics, T's were for electromagnetics, and finally the boosts also in time for gravity. So that they need different energy contributions. What is realized by different lengths of axes. So we have three axes in space. So there is one, the long axis in space for electromagnetics. There is this tiny delta for tiny contribution of twists, like in this QED Lagrangian, that we have very large contribution of electromagnetics and tiny contributions of twists of quantum phase. And much larger contributions of boost. That performing boost is much more costly. Like Hedgehog boost would be no electron, but a black hole. Yeah, so we need to emphasize it in formula that the boosts are much more costly than these spatial rotations, and the cheapest energetically is the twist. Yeah, so this way we have from the dynamics of these twist fields and the boosts, we get electromagnetic quantum mechanics plus gravity coupled. And from the topological excitations, we get the particle menageria as required. So here is, for example, the simple derivation simplified of Coulomb interaction. So we have these quantized charges. The question is, do they get them interaction as electromagnetics as they should? And turns out they do. So here is we just put the two such charges in various distances and integrate Hamiltonian, what gives the total energy. And the dots are the numerical values, and the line is the fitted 1 over distance. And we can see that it's nearly perfect. So we can say that effectively these charges topological get Coulomb interaction. So we get simpler model of electron. Yeah. So now mathematical using this Hamiltonian. I mentioned that it's approximate because, for example, in very low distances, there is this running coupling. If you do it right, we get the proper running coupling behavior known from particle physics. Okay, so I mentioned there is this time crystal. So this is quite non-trivial problem that this resting electron already needs this angular momentum, resting neutrinos need oscillations. Yeah, so in formulas, it is said that we need to use E equals mc square mass as energy in the quantum phase evolution. Yeah, so this is formula used both for the neutrino oscillations and electron de Broglie clock, but there is also angular momentum. So, but we can see that literally the mass of particle propels the clock. Yeah, so we need to use some mass of the particle, but it's difficult to get because naively energy minimization should make the time derivatives kinetic energy to get down to zero. So the question is why the energy minimization leads to non-zero time derivatives. And in the mentioned approach, we get some negative term Hamiltonian. So the full four-dimensional liquid crystals that get also negative term energetic in Hamiltonian, which says that it's preferred to oscillate the time derivative terms in presence of boosts. So the mass, gravitational mass, which corresponds to boosts, gives preference for time derivatives as the clock, as the oscillations. Yeah, so we get exactly the preference we need, that the resting electron has preference to angular momentum, resting neutrinos have preference to oscillations. And here are some fable results of simulation. So we can see that the omega going to 0, let's get 0.8, we reach the minimum of energy. There are some two cases. So indeed, energy minimization leads to non-zero, but also finite omega. Yeah, so we can get it, and the formula automatically leads to it together with the gravitational mass. So here to get we need both the gravitational mass and the oscillation. So also solving another problem, why they have gravitational mass. Then there is Klein-Gordon derivation. So here is the link. Then there is also test for Larmor precession. So it should be linear, but here we can get square. But it got from simulations also this behavior that with increased omega b, the omega increases as in Larmor precession. So yeah, so finally this is electron. So here is more sophisticated simulation of decay of muon. So we have the three leptons, electron, muon and tau, so they have asymptotically the same charge. Yeah, so topologically they should be the same charge, but they have different realization, different mass. So we need, so here is we need Hedgehog for the charge. So but Hedgehog in 3 dimensions have you have first, second, or third axis. You have 3 types of Hedgehog, and here Fabry first tested that minimizing energy from these hedgehogs, we get some stable configurations, local minima. So we get the candidates first for the 3 leptons. And here is such hedgehog of the second axis. Here is the hedgehog of the first axis as our electron. So here is kind of heavier electron. Yeah, so typically the same charge, but of different mass. And now we have asked to kick the dissolution. Yeah, so to apply energy to make it decay, because this is only local energy minimum. And indeed, it performs the simulations going to electron and realizing the energy difference as this kind of excitations, because there are these topological vortices we cannot avoid due to Haley-Boyle theorem. And so, and there are many reasons to interpret this kind of configuration, these vortex loops, as neutrinos. Yeah, so the question is why muon decays to electron and no photon. So what before photon would be just wave carrying energy, momentum, and angular momentum. But this is much more stable. So a neutrino can pass through Earth, photon cannot. Yeah, so this is kind of more stable version of, no, it's not photon. So this particle is very difficult to interact. There are 50 families. We get oscillations between these families. So there are many reasons to interpret this kind of configuration as neutrinos. And here is the configuration. Here is the simulation that we can see that there is very strong localization for this muon, and then it decays, and then there is much weaker localization, and there is some release energy. So then there are these nuclei. I mentioned there is a big problem with mainstream view. There are literally 2 worlds: one the standard model up to proton neutron, and then the nuclear physics with own formulas, general formulas which can fit everything. Like for if you have 3 nucleons, they need three body potentials. For 4, they need four body potentials. So very general formulas, Taylor expansion, which able to fit all and just fit them without understanding. So again, we need finally some hints from deeper level physics. And the hints here are that we need these topological vortices, the one-dimensional structure. There are many hints. So they are used in mainstream physics called quark strings, gluon flux tubes. But we have topological vortices, and quarks are the excitations. Yeah, so these topological vortices are very light, but we can then rotate the field like here. If we perform full rotation, they will be hedgehog. And hedgehog for us is elementary charge. But we can also perform fractional hedgehogs, and this way they would behave as quarks, but we bend them the charge quantization. Yeah, so as mentioned, there is a particular charge quantization. So there is something wrong happening between them. And so it will lead to some additional energy proportional to distance approximately. And this is known in this corner potential, is approximately 1 GeV per femtometer. Yeah, so because of bending charge quantization by quarks, fractional charges, there appears this additional 1 GeV per femtometer energy density, which prevents the escape. So for quark confinement. Yeah, so having this one-dimensional structure, we think they think the mainstream usually think about them only inside proton neutron, but nucleus is multiple proton neutrons very close together and somehow close against the Coulomb propulsion. So there are many arguments that this one-dimensional structure should also kind of bind them. Yeah, so that we should think about nuclei not as back of quarks. They tried with this EMC effect, but doesn't work. Instead, we should think about them as knots of these topological vortices with quarks as the fractional charge excitations. And the best argument for is the Haro nuclei, I think, that we have, there are observed like lithium-11, there is a core and the two neutrons in very large distance, like a few times larger than of nuclear force, which has minimum in below one femtometer. Here we have FUO. So, and they are very stable for milliseconds. So they can be charged, they can be protons. So they are repelling, but still they are staying there for a very long time. And moreover, they need three-body forces to describe them, and they call them Borromean neutrons, like these knots again. That if we remove one of them, the remaining will fall apart. So there are many arguments that there are indeed some kind of knots, yeah. So of topological, there are one-dimensional structures, and they actually help in this binding of these two neutrons, protons for a very long time against Coulomb propulsion if there are protons. Okay, so and if understanding going this way, getting simulations of nuclear physics, I think we should optimize, be able to optimize for nuclear fusion. We currently don't understand, so to get better control of these processes, to get practical fusion, and maybe some other consequences like maybe stimulated proton decay, but in very far future. And to summarize here is so I will talk about simulation of simple leptons, but then we have also neutrinos. There are many suggestions to see them as vortex knots. So leptons as the three approximately the three hedgehogs. And after applying the energy minimization, then there are baryons, so nuclei as knots of topological vortices, starting with the baryons. So maybe let's think about the simplest knots, like here. So we have one vortex inside, second around. And if we take a look at this cross section, you can see that the vortex around deforms the vortex inside and deforms toward hedgehog. And hedgehog for us is an elementary charge. Yeah, so this way we get that the baryons have tendency for electric charge. And proton can just enclose this hedgehog, getting this kind of configuration, but neutron has to compensate it. Yeah, so we have this plus enforced by the knots, by the baryon structure, and now we need to compensate it to zero. So we need the quarks this way. Yeah, so again the quarks are very costly, and to understand why they are happening, here is a nice picture because there are these enforced by structure positive charge, and we need to compensate them to zero. So there are appear quark for this purpose, which add energy. This way, explaining why proton is lighter than neutron because this quark compensation is costly. There the deuteron, so we have the simple nuclei. So mainstream doesn't know, cannot derive from lattice QCD or nothing. And we get the charge quantization. So we have two baryons, both require this plus charge. So we have this plus minus plus. We get the electric quadrupole moment. So as observed in experimentally, my mainstream cannot do from lattice QCD, cannot say anything like this. Ariel, we have this positive core for deuteron and negative shell, also known from experiments. So very simple model, and in the picture we can already qualitatively understand many properties. We can try to understand the beta decay, but the simulations are very difficult. We are trying, but the main difficulty is that we literally the formulas have to work simultaneously on quantum mechanics, electromagnetics, but also on the gravity to get them all these dynamics, the angular momentum of electron, also angular oscillation of neutrinos, angular momentum also in nuclei. Yeah, so static, so minimal. These particles in minimal energy already have some internal dynamics, so we can get it mathematically, but the simulations are very difficult. These are extremely fast oscillations. Okay, so thank you. If somebody would like to help, maybe also this benchmark is open. So if you have promising model or know somebody, please ask to also consider maybe and help developing. And to finally, hopefully, to search these kind of models with AI in objective way. So if there are authors, yeah, I know many who just see on model for decades, so they need serious verification. If there is some promising, we should find this way. And if human candidates will be insufficient, then AI could further search for a better model. Yeah, so maybe learning on these models, kind of training, based on which it will search for the better one. So I think it's a matter of time when we get this one level deeper, but it shouldn't be the final one, the final level. As for example, here we need the potential still, and potential suggests are usually effective. So probably there is even deeper field level which will allow to derive these parameters, like 3 parameters of this inside this potential. So there is will be still a lot to do. But again, maybe to be human model, maybe AI will just search the possibilities and maybe self automatically and find the better model. But there might be last time for humans to really participate in this research. Thank you for the attention.